Hello everyone, my name is Michael Tuis, and I want to first apologize for missing you all last Tuesday. I was out all last week with severe food poisoning, so I was not doing much of anything, let alone giving a presentation and speaking. So we decided to kind of record this virtually, throw it online for y'all to watch it on at your leisure. So I want to first thank you very much for taking the time out of your day to watch this. And to let you know, if you have any questions, please feel free to put them in the comments below. I'll try to answer them as promptly as possible, and we can kind of have a back and forth conversation down there. So without further ado, let's hop right into it. So the goal of our project was to make a near IR solar simulator to characterize next generation solar cells. This is in collaboration with the National Renewable Energy Laboratory to expand some of their research capabilities in this space. Now, specifically, what we kind of care about is in solar research right now, there's been a huge push in trying to understand next generation solar cells and materials, things like perovskite and cadmium telluride solar cells, due to their high efficiencies relative to silicon. But right now, there are currently some barriers in actually being able to probe some of these properties. And one of these barriers is in solar simulation, which is basically the process in which we take a very fancy bright light, we put it in a box, and we pretend that it's the sun. And we put solar cells within that box, and we can get electrical properties and other types of properties that we care about from that type of simulation. And what this kind of looks like right now is this is the current state of solar simulation in the world right now. The black line right there is the AM 1.5G spectra, and this is basically what you might experience on a nice sunny day if you go outside and just on your bare skin. That's what the sun looks like on the surface of Earth. And what we try to do is we try to simulate that to the best of our ability. Now, that red and green line there, though, is what is conventionally used in solar energy to actually simulate it in conventional solar simulators. And as you can see, that doesn't really match up well with that AM 1.5G spectrum at all. And this kind of is one of the problems. This is good enough for silicon, for measuring silicon and what it was based on. But if we throw on our kind of next generation solar panels and the areas that we care about, you can see that is incredibly messy. It doesn't really match up at all, and it doesn't really represent the kind of solar properties and solar intensities that we care about when we're using these devices. So we wanted to solve this, and the best way to solve this is to make a new type of solar simulator. How are we planning to do this? We plan to take a technology from a 2014 paper from Nakajima, where they basically were able to make a solar simulator using a UV LED and a ton of phosphors, which are just materials that emit a specific wavelength and a specific intensity when you excite them with some sort of light, in this case UV. And what they did in this paper is that they were able to actually combine these phosphors together and recreate the AO 1.5G spectrum really closely. As you can see on the graph on the left there, that's that red line that's matching up really closely with the black AM 1.5G spectra. And they basically did this by taking all the phosphors that you can see on the right there, which is really great, and this is really good progress, and this is really good for silicon. The only problem is that it still isn't getting into that near IR region that we care about, that 800 to 1,000 region that we really want to probe these new materials at. So the goal of this project is to try and find some new materials that we can hopefully expand out that near IR capability, combine that with this existing technology, and hopefully get a really good solar simulator that we can use to actually characterize some of the devices that NREL is making. And kind of the main way we hope to design this in a very simplified fashion is when we're looking at the solar simulator, what that's going to actually look like at the end is it's going to have, a 365 nanometer LED circuit board that's just kind of the best UV light to provide excitation in this case, a cooling plate and a loop to allow us to really get a high intensity. Again, we're trying to simulate the sun. That's a lot of power that we need. You're still using some of the copper tubes, and then a 1 square inch area mask, which is when we're talking about a phosphor mask in this case, we're just talking about a piece of glass, and the phosphors suspended in some sort of silicone matrix, just pasted on top of that glass. Nothing fancy. It's not rocket science technology, right? We're trying to make this as simple as possible so we reproduce it as easily as possible. And the goal for this experiment was that hopefully we can make 5 masks using these brand new near IR phosphor materials that we have, and we can basically test those and create those to kind of compare them together to find the best phosphor mixture and use that kind of further for testing and then for further development of this type of technology and this characterization, um, and to allow us to further optimize it in different ways depending on what type of experiment we're trying to run. There might be different materials that work well with other certain types of next generation solar materials, right? Maybe we want to use different masks for perovskites versus cadmium telluride, for example. We don't know, so that was kind of the goal, make all these 5 different masks. But one of the things that kind of happened with this project is that our goals have now changed after learning a couple key lessons and running a couple key barriers that we had to overcome. So let's dive a little bit more into what I'm talking about with that. This is our general simplified flowchart that we had when we kind of started this experiment. The goal was to basically make a ton of powders, synthesize them, run XRD to basically get the purity of these powders to make sure that we actually made what we wanted to make, blade coat all those powders once we knew what we made, and then use PL spectroscopy to basically get those emission spectrals that you saw on the slides before to be able to slide all those pieces in together in a puzzle piece to design and make the masks using the same blade coating method that we use to be able to do PL spectroscopy. And then we would obviously take those masks, throw them on this solar simulator that we built, and bam, we have a nice functioning solar simulator. The only problem is that it's nothing is ever that simple, right? So we hit a couple key barriers that really halted progress and things that we had to overcome. But this is really actually a good thing because these barriers have really given us a much better understanding of how to actually build out this technology, and it's allowed us to really get well set up to actually scale up and optimize this technology moving forward. So we have a lot of permanent equipment, a lot of permanent procedures now that if we want to go, ideally, for example, if we want to go past the 1 square inch area, let's say if we wanted to make a whole solar simulator to characterize a whole solar panel, we now have that infrastructure kind of ready to be able to scale up very easily. So let's hop into some of the barriers though. Let's talk a little bit more about what we learned and how we overcame them. We'll start out with talking about how we synthesize powders and what these furnace treatments look like. So we basically just took a clump of powders, mixed them together in a nice little aluminum boat. We threw them in a furnace at a high temperature with atmosphere, and it comes out and we get a nice chemical reaction. So as you can see from these initial powders that we made very early on, these aren't very well mixed. They're not very good powders. So what we started up doing is we threw them in a crucible that mixed them up really well, and that really solved that issue and made it a very homogeneous powder. The reason we didn't do this starting out is because we really wanted to start from the very basics to really get understanding of how to work with these powders and how to really build out this technology from the ground up. Because hopefully we can reproduce this and optimize it and really mess around with this moving forward to kind of make this a very developed technology if this works out and if we can prove this technology can actually work in the case that we want. So we made these nice little powders by just mixing them and crushing them in a crucible and doing a furnace treatment. These are our 13 secret spices that we use to make all the phosphors. And this very basic procedure of just throwing some powders into a furnace was working really well until we hit our highest temperature treatments. That's those 1300 degrees C treatments right there. And as soon as we started doing treatments at 1300 degrees C, we started seeing we ran into some issues. Specifically, when we took our powder, our reagent powder here in our aluminum boat, and we threw them in the furnace, we got a reaction. We saw the powders melted, they mixed together, and they reacted, right? This is all really great. But another reaction that occurred, another kind of chemistry, was that they started wetting to the aluminum boat. And by doing this, they completely adhered to the aluminum boat to the point where we could no longer remove the phosphors that we made from our furnace. So basically, they're entirely stuck there. There's no way to remove them whatsoever without a massive amount of effort and heat and mechanical stress, right? So that's not really ideal if we want to make a ton of these powders and really scale it up. So we had to come up with a solution. We first went to the literature to try and find a solution. None of the papers that were referenced in the construction of the original solar simulator mentioned this issue. So we kind of had to come up with our own solution, which was really great. And we decided to try a different type of boat. So in this case, we chose a boron nitride crucible because it has different wetting properties relative to alumina. So ideally, this would mean that it wouldn't wet. Our powders would not have the same wetting effect in this new type of crucible. So we tried it out, and it turns out, yeah, that assumption was correct. And by using these boron nitride crucibles, we were actually able to see dewetting that allows us to really easily pop the phosphors out of the actual boat itself, and we're now actually able to synthesize these high temperature phosphors, which is really exciting. The only problem is that this problem was solved and this dewetting experiment was run last Monday, so the Monday before the presentation was going to be given. So this is a really recent development, and we're kind of just going through and trying to make the rest of the phosphors using this lesson that we learned. And now we're kind of making these phosphors and going through all that stuff, right? One of the things we are going to do after that is XRD. And the immediate barrier that we hit with XRD was that the X-ray diffractor that we're going to use broke right before we were going to use it. So this meant that we had to basically construct a brand new powder setup in an XRD that nobody else was using, which was pretty fortunate. So we found this XRD, this Ultima 4 that had been scarcely used in the past. We asked the owners if they'd let us, if we would be allowed to set up a powder setup. So we constructed within that. We did all the safety trainings and stuff like that. This was completed again the Monday before the talk. A lot of this stuff ended up, strangely enough, happening almost right before the presentation was to be given. And basically, what this meant is that we constructed an entire powder setup to be able to do XRD for this project. That's a really great result. That's really awesome. But it definitely meant that we weren't able to do XRD yet. So we still don't know if we made what we wanted to make. And that's kind of one of our next immediate steps right now in the coming weeks is to get this XRD going and to really just run through some of these scans. So that's what we've got a ton of these little zero diffraction plates to be able to do powder measurements on. Basically, they're just these little silicon plates that we can just throw our powders on and not worry about any sort of background. And then we're just going to do some basic purity analysis using mercury and Igor just to make sure that we made what we want to make. For PL spectrometry, we had a very similar story as XRD where we had to build out our own setup. We did have a PL spectrometer that we could use, but it did not have a UV setup. So we had to get a UV light source and power source and all these things that we required to build it out. And we were able to do this. We were able to get a couple of UV light sources. We were able to really get a couple fibers to connect all this up. And we conducted safety training the Friday before the presentation. Again, a lot of stuff ended up happening at the same time. And what we learned of the safety training, however, is that this PL spectrometer that we had assumed would be certified and had the safety precautions to actually be able to do UV excitation like we wanted, did not have that safety protocols at all. So the main reason why is that they've since modified this to actually do an open air PL spectroscopy, which basically means that you throw the laser and then you get a result straight back at you. The only problem is that people get nervous if we have an open air UV light source. It's not good for your eyes or skin. So what we're having to do now is we're kind of building out the safety apparatus and the safety containment to actually be able to do this and completing all the appropriate paperwork to be able to safely operate this. But once we get that completed, we'll actually have a really good permanent system that we can use for this experiment moving forward, which is really exciting. Blade coating is probably the simplest story here. It's good to go. We have a nice lovely piece of glass that has, it's a Corning SG7 glass that we use to actually make modules themselves. And it has really good UV transmittance at the area that we care about, which is that black line there. And we have plenty of silicone paste ready to go, Silgard and RTV to basically be able to make and blade coat these on. Basically how this is going to work, we're just going to take these, mix these together, mix the silicone with these phosphors, and then just take a razor and just basic razor and coat them onto these pieces of glass, and we'll make as many masks and phosphors as we'd like in that regard. This is a relatively simple part, and this is all good to go. So as soon as we can get all the other steps done, we can do this. Which, speaking of the next steps, right now we have a ton of permanent equipment we need to use, and we plan to use them. So what is kind of left of our goal for getting to the point where we can actually characterize all these phosphors and start thinking about designing masks is a few days of characterization and a few days of making stuff, right? And it might be realistic to actually get that done by the time the final report is due and the class is over, but it will all depend on the safety parameters and what's going on with there and how long that takes. So our new goal right now is to have each mask designed for the final report to hopefully be able to get through all the PL spectroscopy on all the powders with blade coating and XRD completed. We'll see if we can get there. I'm optimistic that we can, but we'll have to wait and see. After we kind of finish it off with this class, we're going to be working with the client to make materials and masks so that they can further develop the product moving forward through May 21st. And then as we kind of get to the point where we can prove that this technology is viable, the client will then use the equipment that we've built up and set up and all the materials that we've made to actually construct the solar simulator itself and then begin doing several levels of optimization to hopefully get a better spectra for their needs. And with that in mind, the goal is that by the end of the summer, we'll have a functional solar simulator that that NREL will be hopefully able to use in their experiments. So to kind of summarize really quickly, we hit several barriers to halt of progress, but the project is on track for completion in the next few weeks. We're not sure about how the timeline of some of the experimental setups will go, and we should know soon if this is a viable technology. And if it is, our client will take over on that regard. Thank you very much. This is the end of the talk. Thank you very much for listening, and I hope you have a good rest of your day.